Uh, Hello and welcome to all students. This is first year BSc class, and today we are going to solve some examples on differentiable functions. In the previous example we have shown that the every constant function is differentiable on the set of real numbers. Now in this example, in this lecture, we show that the uh, function f of x equal to x raised to the power n is also a differentiable function on the set of real numbers. So let us write the example. Let f from r to r be any sorry not any be a function be a function be a function defined as that function is defined as f of x is equal to x raised to the power n. And what is n here? N is any natural number and it is defined for all x belongs to R. Okay, for all x belongs to R. Full stop. Show that f is differentiable at every point in R. Our question is show that f is differentiable at every point in R. Okay, so let us try to show that function is differentiable at every point in R. Okay, so let us write the answer of this problem. So first of all we write what is given to you. Given that f from R to R function defined as f of x is equal to x raised to the power n, and it is defined for all x belongs to R. And what is n? N is any natural number. Okay, and we have to show that function f is differentiable on every point in R. So let us take p belongs to R be any arbitrary point, be any point in R, and we show that the function f is differentiable at point P. So consider the limit as x tends to P of the function x raised to the power n, or we can say consider the limit f of x minus f of p whole divided by x minus p, and the value of this limit is equal to limit x tends to p. We try to solve this limit. Okay, we try to solve this limit. Okay, so f of x is x raised to the power n minus f of p is p raised to the power n, and denominator is x minus p. Go to the next step is equal to limit x tends to p so just factorize this term. So this term has two factors. First is x minus p, and second factor is x raised to the power n minus 1 plus x raised to the power n minus 2 into p plus x raised to the power n minus 3 into p square plus dot dot dot. I will write that last factor here, p raised to the power n minus 1 bracket complete, and whole divided by x minus p. So this factor x minus p will get cancelled with this x minus p, and it is equal to limit x tends to p okay, and it is equal to again, so numerator is okay, there is no denominator now, denominator is cancelled. Okay, so there is only a term x raised to the power n minus p plus x raised to the power n minus 2 into p plus x raised to the power n minus 3 into p square plus dot 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 plus p raised to the power n minus 1, it is equal to okay. So in this function, instead of x put p, then you will get p raised to the power n minus 1 plus okay, p raised to the power n minus 1 plus here again p raised to the power n minus 1 plus third term is again p raised to the power n minus 1 plus dot 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 plus p raised to the power n minus 1. So we have these are n terms, therefore n into p raised to the power n minus 1, and this exists okay, exists, therefore the limit exists, therefore we can say that the function f is differentiable at point p, and therefore f is differentiable on R, and derivative of function f at point p, the value of that derivative is n into p raised to the power n minus 1. Okay, so okay, at point p. Now let us try to solve next example. Okay, so I will let us try to solve next example. Next question. Next example is example number 3. Question is if f is a function from set of real number to the set of real number, if f from R to R is a function defined as f of x is equal to e raised to the power x, okay, and it is defined for all x belongs to R. Okay, our question is show that f is differentiable on R. F is differentiable on R. So again, we use the definition of differentiable function to show that f is differentiable on R. Okay, so let us write the answer. So first of all, we write the given thing, given that f is a function from R to R. Okay, and it is defined as f of x is equal to e raised to the power x, defined for all x belongs to R. And let us take P belongs to R be any arbitrary point, okay, in R, or it is any point. Okay, now consider limit. Consider the limit of function x, limit as x tends to p of the function f of x minus f of p and whole divided by x minus p. Okay, so if that limit exists, then we say that function is differentiable, and the value of that limit is nothing but the derivative of that function at that point, at point p. Okay, so let us go to, okay, let us evaluate this limit. X tends to p. Okay, so what is f of x? F of x is 1 minute. What is f of x? F of x is e raised to the power x minus f of p is e raised to the power p whole divided by x minus p. Okay, it is equal to limit as x tends to p. Okay, and again now we simplify this numerator and denominator. Okay, so let us take e raised to the power p outside, and so what will be the inside the bracket? E raised to the power x minus p minus 1. Okay, minus 1 and whole divided by x minus p. Okay, so as e raised to the power p is a constant, take outside, and the limit of this remaining term is, we know that the limit is log of e. Okay, log of e. So finally we get the value, and okay, e raised to the power p is the value of that limit, because value of log e is 1. Okay, and that exists. Okay, that value exists. Okay, therefore the limit exists, and we can say that f of x is equal to e raised to the power x is differentiable on R, and the derivative of function f at point p is equal to the e raised to the power p. Okay, so this thing. So in this lecture we solved two examples based on the limit of a derivative of a function, and this is the end of this lecture. And thank you very much for paying attention.